Good afternoon, everyone, and thank you all for joining us today for this the 10th webinar on the cycle of nuclear fuel, which is going to be presented by Bakhtiyar. And before we start, I would like to invite Astu Samprativi to tell us more about Emanate and its activities. Followed by that, I will be talking a little bit about Bakhtiyar, and then I will hand over the stage to him to talk to us today about the cycle of nuclear fuel. Thank you.
So yeah, hello, my name is Astu. So welcome for whoever is joining on Hangout and whoever is joining on YouTube. And yes, today on a sunny day here, at least in France, we're going to have the 10th webinar on the Emanate webinar series. And this time it's going to be by Bakhtia. But before, I would like just to give little introductions about what is Emanate, especially for those who are joining for the first time or listening to our recording for the first time. So yes, Emanate was created by 2017 graduates. I think I should stop saying that, but it was created in February 2018. And at the very beginning, we wanted to learn about what others were doing during their internship projects. So we created series of webinars, and then we thought of like expanding this so everyone could benefit from what we are doing. So that's where we actually created all the groups in LinkedIn and in Facebook when we are connected to each other. And until now, what we did was like we are doing webinars, and we are also starting with the Emanate Digest, and we already released the second issues of the Emanate Digest. And in the future, we would like to have also a podcast and a website where you guys can refer to our activities. So our webinars covers a lot of topics. Basically, it really depends on the volunteers from our community, and it covers from the biomass, from life cycle analysis, for solar and technologies and all, including also the startup. And the last webinars that we had in 2019, which was the first in 2019, was about forecasting rural energy demand in developing world. So all these webinars, you can go to YouTube and you can see the recordings, and you can benefit from the knowledge sharing from there. So we have a LinkedIn group and a Facebook group, and also a list of the previous webinars, and we invite you to go there, join us, and watch the webinars. And on the other hand, we also need you, because all the activities really depend. It's based on volunteers, so we are doing it on the free times. So the more manpower we have, the faster we can grow together. So we invite you and your expertise to become either a webinar speakers or to write paragraphs or articles with us, and also in the future for to be our podcast speakers. And also, if you are experienced with building websites, we could also use your experience on that. So yeah, I mean, feel free to join us and write us either on Facebook, LinkedIn, or on our email address. And yeah, well, I will give the time back to Nipun and to Bakhtiar. So enjoy, guys.
Hello, everyone. Thank you so much, Astu, for presenting a minute to us. And today we have among us Bakhtiyar, who is an assembly fuel engineer. So Bakhtiyar is currently working in a manufacturing plant of fuel assemblies in Kazakhstan. He is responsible for establishing the manufacturing process, equipment, and related operations, as well as the working instructions. Today he's here among us, and he's happy to share and talk to us about nuclear fuel cycle. He finds this topic really important because he understands that there is a really a big need to better understand the principle of nuclear fuel cycle and how nuclear energy works, and how there is a potential for this energy to collaborate with renewable energy in the next 50 years. Before I hand over the stage to Bakhtiyar, I would just like to remind our viewers of some basic principles, that in this webinar you are free to ask questions whenever you like. For those of you joining us on YouTube, do not hesitate to use the YouTube chat to its very best. Please tell us who you are and where are you from, and also if you have any questions, do not hesitate to ask them in the chat window, and I shall pose it to Bakhtiyar on your behalf. Also, the last point, we just want to make sure that this webinar is actually not a debate between for the fact that is nuclear a viable option or not. This is just a webinar to better understand how nuclear energy works, so that we are capable of having this debate probably in the near future, but not in this webinar. Thank you so much, and I invite Bakhtiyar to please present to us the nuclear fuel cycle. Thank you.
Thank you, Nipun. Thank you, Astu. It was a pleasure to hear you all. Even though you have a wonderful day right now in France, it's already dark in Kazakhstan, and just sitting at, okay, the time is 7 p.m., so we have 5 hours difference. I'm working as a fuel manufacturing engineer in the east of Kazakhstan, which is not far from the border of Russia and China. So if you look at the map, you can find my city. It's called Uskyanogorsk, Uskyamen. Before I start, I would like to just confirm you can guys hear me well. Guys, can you hear me?
Yes, we can.
Wonderful, thank you. Well, I don't know how many people are currently watching us, so I'll just try to start. I tried to prepare the presentation as fuel assemblies and for the fuel cycle, because even though most of you guys are from the PM3 or from EMI3 majors, you are all about focusing for these renewable energies. I also agree with this, but in the meantime, I think it's need to better understand the fuel cycle for the nuclear fuel. It's also a kind of good source of the energy. It's a transition between, let's say, CO2 emission energy sources and the renewable energy sources. All right, let's get started. Currently, you all probably know me from the SNIM class, Institut Mines Telecom, Atlantique in France. I did my production industrial application, originally from Astana, but currently I'm working 100 kilometers away from my home in the East Kazakhstan as a joint venture in the clean fuel production plant. Okay, so how do we get the nuclear fuel, guys? Nuclear power. Nuclear fuel first is a fuel in nuclear reactor that sustain a nuclear chain in the reaction. So most common nuclear fuels are uranium-235 and plutonium-239. One uranium fuel pellet can give the same amount of energy as 1 ton of coal, as 149 gallons of oil, and 17,000 cubic feet of natural gas. So it's one fuel pellet you can see in the picture. So get back to the basic principles of the chemistry. We have light elements starting from hydrogen, and if the switch in the hydrogen transition from hydrogen to lithium and to beryllium and so on, it gives a lot of energy. So this process when they called fusion. Another time when we have plutonium, we have uranium, neptunium, and thorium. These radioactive elements, when they switch in and releasing, changing their atomic levels, they can create, gives also energy. So this process we call fission. So today we're going to talk mostly about the fission. Basic principle about uranium. So we take uranium as the main well-spread material for the nuclear energy. It's a radioactive metal and consists of isotopes. 99% of them are uranium-238. 0.7 isotope is uranium-235, and the rest is uranium-234. But for starting the nuclear chain, we just need uranium-35. This is very small amount. And mostly to start a nuclear reaction in a reactor, we need around 3 or 5% of uranium-35. Reaction starts with one unstable neutron. Imagine when one neutron passes through and hits the target nucleus. This target nucleus produces 3 additional neutrons. The next neutrons produce hits another fission product, and so on. This gives you enormous chain, like avalanche of neutrons coming. All this process gives a lot of heat, a lot of energy. The nuclear fuel cycle is a series of industrial processes which involve the production of electricity in nuclear power reactors. We start from 2 types of cycles. The first is an open cycle, and second is a closed cycle. Open cycle considers that we mine and mill uranium, then we convert, put it in conversion, enrichment, which I said before, enrichment is the switching from the 0.7% to the 30%. So we need to enrich to this level. Enrichment, then fuel fabrication, light water reactor, the interim storage, and geological disposal. But the nuclear fuel and nuclear energy now and engineers are focusing for the closed cycle, which includes reprocessing and recycling the waste. So as long as we finish with the light water reactor, we put in spent fuel, then out of spent fuel, we can reprocess, reproduce again to make another fuel fabrication and put it into the advanced reactor, which is our building right now. So they go in the closed cycle. So the waste can be used. But some of the waste, of course, cannot be used for sure. It's a high-level waste. So it's need to put it in internal storage. And then after some time, it need to go for geological disposal. So this is how the nuclear fuel cycle looks like. As I said before, starting from the mining, the conversion to UF6, uranium hexafluoride, then we have enrichment, fuel fabrication, reactor, storage. Some of them goes to disposal, but some of the waste can go to reprocessing. They produce we took some plutonium from this waste, put it into the MOX. Also enrichment, some uranium can be put in the MOX here, and then we have closed cycle circulating here. Some of the reprocessing waste cannot be reprocessed, and only we can do now is just to vitrify them, put it into the containers and bottle in the like glass, special type of the glass, and go down deep disposal. Uranium, we start from uranium mining first. This is how uranium looks like. It's like a stone, uranium ore. And there's 2 types of uranium mining, excavation and in situ leaching. They both focusing on recovering the uranium ore. The top uranium U308 producers as a tons of uranium is a Kazakhstan 39% with 23,000 tons, then Canada 22%, Australia, and so on. Niger, Namibia, Russia, Uzbekistan, and US. First is the excavation, uranium mining. There's 2 also types for the open pit mining. It should be close to the surface, and unfortunately it takes a large size of the surface, so it gives a lot of work to do. So this method requires large quantity of materials to prevent the pit slopes from the collapse. Another second option is underground mine that goes deeper than 120 meters, but the good thing is they have small surface disturbance and less quantity of materials needed. But also this method requires special precautions, consisting primarily ventilation, protection of the airborne radiation, so it's kind of dangerous to work this way. And then the second method for doing this, and mostly widespread, well spread in the world, people prefer this because it's less dangerous for the workers. It's uranium leaching from the ground. So this is the process how it works. So there is some plant of the uranium above the uranium bearing sand. There's some oxygenated groundwater is circulated down deep to the uranium, let's say like pit, bearing sand. It mixes well in a very porous outer body, and to dissolve the uranium oxide and bring it back to the surface. Where's the plant? And then there's a filtration, there's a separation, so the plant receives the uranium ore and the rest liquid goes back again and circulates. This is called in situ leaching. Then from after this, we extract the uranium from the ore. If it's open or underground mining, so we need to crush this and soak into an acid solution to leach out the uranium. And after drying the pulverized ore and filtered, it can be concentrated into uranium powder called yellow cake or urania. So this is how urania yellow cake in a steel drum looks like. It consists of 70 and 90% of uranium oxide, U3O8, and also there's some percent of the uranium dioxide and uranium trioxide, but the majority of this uranium 308. So around 200 tons of this uranium 308 is required to keep a large 1,000 megawatt electricity for 1 year. Then the next step is uranium conversion to UF6. Since only around 0.7% of natural uranium is fissile, which is uranium-235, but we need 3.5 or up to 5% of concentration of fissile uranium is needed. So this enrichment process requires uranium to be a gaseous form. First, uranium oxide, U3O8, is refined to uranium dioxide, which can be used as a fuel for some types of reactors. The rest is converted into uranium hexafluoride, which is UF6. So then this UF6 in a gaseous form need to be placed into this like tube circulating very in a high speed, very rapidly. Sometimes we call it centrifuge. And then in this physical circulation, the heavy elements, let's say uranium-238, goes far because it's heavy. On the side?
I have a question.
Yes, sure.
So how is the uranium converted into gas? What process is like in a boiler or a pressure or?
A good question. Well, it's milled so well, and I think it should be dried very well in like a boiler. Okay. Honestly, I cannot tell you for sure the exact process of the conversion.
Okay.
I need to tell. Well, I'm not gonna lie. I don't know.
Okay. All right. That's okay. We will have.
I know this. It's been turned to the hexo. All right. After uranium enrichment, when we rotate too fast, we separate the uranium into the 38 and 35, which is 35. It's in the center, which is easier for us to separate. So if we left with the heavy uranium-238, it can be considered as a depleted uranium. So far, it's not being used as a fuel. It can be stored temporarily for the next possible processes. After this UF6 cylinders use the vaporization to create the gaseous form, then it's used for uranium dioxide production, uranium-35. And this is how the process for this fabrication looks like. The next step will be powder processing into the pellets, as you've seen before, the small black dot like cylinder. And then these pellets can be used to produce the fuel rods, fuel assemblies. It's kind of process where I'm working right now in Kazakhstan. And then it can be transported to the nuclear reactors.
So the question is, another question.
Sure, go for it.
Okay, so it means first you on the centrifuge you have one output as uranium-238, and then you have uranium-235, which is UF6. Is that correct?
No, first we have the input is UF6.
Okay.
And then UF6 uranium has different isotopes, uranium-235 and 38.
Yes.
Inside. Because majority of this is uranium-238.
Yes.
Right? This one.
Yes.
So we have two in natural uranium.
Okay.
So
okay.
Because it's heavy and it's majority of this, they have more atoms.
So after the enrichment process, you have actually a UF6 with 3.5% of uranium-235.
Well, UF6 is inside. So we centrifuging UF6,
Yes.
and yeah, they have some also hydrogen HF, hydrogen fluoride.
Uh-huh.
It's a separate material, but we're only focusing now for the uranium that we produced. So
Yeah.
the enriched uranium is going one way, and depleted uranium another way. So it's basically a
Okay.
separation of the UF6.
And this enriched uranium is in the form of gas as well?
It's yes, in the gas, but
Okay.
then it can be I don't know the process they do here to do there to produce the powder and the gas of UO2,
Okay.
uranium dioxide into the powder production. So
Okay.
this is another step here,
All right.
which is I don't know because I never worked. I work in different section, but
Okay.
I need to make deep research about this.
Okay. Well, thank you.
Thank you for asking. It gives me like a feeling that I'm not talking alone as a presentation. All right, we continue how nuclear reactor works. You've pretty much seen this image before. So this is the containment structure for the nuclear power plant. There's inside of there's a nuclear reactor, and there's a circulating loop of the hot water that passes through the nuclear reactor. There's a pressurizer. You see the red color because it's super hot, and there's a pump circulating it. And then the next cylindrical container here, it's a steam generator where the water boils through this loop. It receives the heat and produces the vapor. So this vapor goes here to turn the turbine, and turbine turns, it produces generated electricity. But the vapor which comes here, it's cools down and drops into the condenser. But to increase the speed of condensation for the vapor, there's another third loop of the clean water. So it cools down and produces continuous circulation in every 3 steps. And if you remember the Fukushima accident, what happened, this is outside container which is circulating here was crashed by the tsunami. So there's no water to circulate in the Fukushima. So this reactor got it too hot and it stopped. So now the modern nuclear power plants, they preventing all the loops and all the parts of the nuclear power plant from the external factors. The question?
No, no, not
No.
from me.
Okay. Thank you. All right. So this is where I'm kind of good at because I'm working in this. This is how the fuel assembly looks like. So inside a fuel assembly, it has different designs, so many different designs. It consists of the fuel rods. So this is a fuel rod where the small pellets are located. It can be, I don't know, 200, almost 250 fuel pellets in one fuel rod. And these fuel rods are combined into the fuel assembly. So one fuel assembly contains 264 fuel rods. It's mostly like 17 times 17 design. And the rest, 25, are used for this control rods guide timber tubes. In case of the emergency, it can be used during the external reactor shutdown. And there's a bottom nozzle rod cluster system where it goes into the fuel assembly to stop the reaction if necessary. So this fuel rod and what else? So one reactor contains around 145 to 193 fuel assemblies. And this fuel assembly is functioning, maybe giving the energy for a year or year and a half. This is also fuel assembly looks like in a reactor. So it drops into this in the reactor core, where the water passes through these fuel assemblies, receiving the heat. This is a different type of the fuel assembly because it's hexagonal, 6 angles. It's a Russian VVR reactor. After this used receiving the energy from these fuel assemblies, after 1 year and a half, used fuel is produced and still contains 96% of the original uranium. Also, 1% of them is produced as plutonium, and the rest 3% is considered as the waste to be solidified. So reprocessing is removing uranium and plutonium from the waste. So starts by chopping the fuel rods and dissolve them in an acid to separate several materials. So this way we can recycle the uranium and plutonium to the new fuel. So as I said before, when we have uranium-238, which is not being used during the production, it's considered as depleted uranium, which is left from a long time ago. So this uranium-238 from depleted uranium can be used to produce a new type of fuel. So if you remember, like basic the chemical formula, when we have 238 plus one neutron, it gives you 239. And this, after several minutes, 239 transforms into neptunium, and this neptunium, after a couple days, turns into plutonium, 239. And this is exactly what we need to, which is gives us good energy in future. Also, there is a fast neutron reactors are capable to transform uranium-38 to plutonium-39 by using this formula. So this is how from the waste or depleted uranium we can make a new fuel. So this is how it looks like. So this is a special type of, it's called fast breeder reactor. Typically, it's based, I mean, the same reactor I showed before, but in different way, except for these yellow blocks here. These yellow blocks, we call them blankets. So the bricks of uranium-238 are located around the reactor. So when the typical reactor functioning gives some energy, producing nuclear chain. So this nuclear chain produces a lot of neutrons. So neutrons are shooting into this blanket. So then uranium-238 receives this neutron. It can be turned into plutonium. So then we can remove it and use it as plutonium-239. So then, after producing the plutonium-239 in a form of plutonium dioxide, together with uranium dioxide, we can form into the mixed oxide fuel, or simple MOX. And MOX is widely used in France, almost in all French reactors. Probably right now, guys, you're sitting in watching this presentation in Strasbourg and Paris, and energy that you're using right now, it's monitor screens, are coming from the nuclear fuel, especially from the mixed oxide fuel. And according to Framatome, is a French company, 8 used fuel assemblies reprocessed may create one MOX fuel assembly. But there's another topic which is very, very important for nuclear energy. It's a waste. And we classify several types, maybe 6 levels, but I just focusing on the most important 3 of them, which is low-level waste, like glass and tools, and some instruments being used for production and operating of the nuclear power plants. Then there's intermediate level waste. They have radioactive materials like less or equal to 31 years. And then the above 31 years, they call them high-level waste, which is they're like very heavy and dangerous, and they need to be definitely stored, not properly stored, but disposed very safely and secure for the environment. So this is called disposals of the HLW, high-level waste. They put them into special like containers in several layers. Mostly those containers they're resistant to the corrosion, and they're resistant to the radioactive materials, to like impact from the radiation. And then they placed into the special mixture of the glass, and they placed into the clay deep underground. It's very biggest, I would say, disposal area, disposal facility that we have visited during our master studies in France. It was in Aube Département Aube, close to, I think on the way to Dijon. Maybe you can take a look. And then there's a facility and goes deep on the ground, like a shaft, which is like 500 meters down deep. And they have different like tubes for these containers to be stored. And as believed, they explained to us the volume of this disposal area is capable to keep all the waste produced from the French nuclear reactors.
I have questions, but
Sure.
I have questions from the previous slides, but let me just ask this first. So,
Mhm.
no. Next one, please. No, the next one.
What is about?
The
Which
about
LV?
geological, the storage of the waste. Next.
This one.
Yes.
Hmm.
So these are buried underground, right? You said.
The deep underground, yes.
Yes, and what you were showing before is actually how to say, like, are the people going in to store it, or they have developed some automatic to actually fill these lines with the waste? How do they
Well,
get this waste to be planted in there?
well, there's an elevator that goes down. So it's also, well, the containers are very safe, so we can easily stay inside because it will well protected. It's
Okay.
secured from the leakage, from the uranium, from radioactive radionuclides, I don't know, radiation or something.
Yes, yes.
And so basically, there's a people like machine they put under on a like elevator. It goes down deep, and then it can be easily transferred to necessary area. So then it will be like numbered. I would say like almost looks like a database, so you know where it located
Right. So
the
people
space.
people actually go in down there, and
Yeah, yeah. We also visited. We seen it's like a city underground. They have like cars, their trucks around going around. They move in these containers. They can place them where is need, and then it's plugged.
okay.
So these containers need to stay longer as much as possible,
Yeah.
and for the next, for the let's say for the best moment, for the better moment when our technologies can be maybe capable to do something else with this high level waste
Um.
in future.
Um, and this facility that you visited in Dijon, you said?
I don't know exactly because I'm not good in this region. It's north of close on the
But
way to the Strasbourg.
no, my question is, what do you think, like, for the context of France, are the geological disposal of this? It's enough to contain the waste of one nuclear power plant or two nuclear power plants, you know?
Of all nuclear power plants, including the all produced fuels. Remember, I said fuel assembly is gives the energy during the 1 year and a half, and this disposal area contains the all year operation of the nuclear power plants of entire France. So right now in the France is around like 59 nuclear reactors, and during all their production lifestyle, they have this facility to capable to capture, to hold, to dispose the entire produced waste. Because
Okay.
what we say about the waste is not only uranium as a fuel, but they're also like pipes, like these materials, all this stuff, reactors,
Yes, yes.
buildings. They also need to be stored there. So this is a huge, very huge underground disposal facility. So we believe that in future, and when our technology, our knowledge will be capable to do something else with this disposal. So maybe we can transfer it again to for another fuel. Maybe
Okay.
we need to dispose and make sure there's nothing geological like factors, let's say earthquakes or some other else, are not hitting. So this to choose this area for dispose. They simulate it in advance for next generation, next years.
Yes.
Make sure there's no earthquakes will happen here. So they put it mostly in mountainous um, regions, so deep underground, to where there's no
Okay.
earthquake. All right, so how many reactors do we need for a large city? So let's say, imagine this is one reactor for it's giving 1,000 megawatts electrical megawatts, and it's enough to supply a city of 1 million inhabitants. Meanwhile, for example, I'm not good in renewable energy, but I think the average power turbine gives around 500 kilowatts. Correct me if I'm wrong. I think it's 500 kilowatts. So to supply a 1 million city, we need to have 2,000 wind power turbines, more than this, 2,000. So it will require a large area. It will have environmental impact on the nature, on birds, on animals, and requires a lot of materials, maintenance, supplies, so much work. But then Wind power is also good as a as a nuclear energy, and solar. It's producing less CO2 emission. I think you're pretty much good in this, more than me. So how many nuclear reactors operating right now in the world? There's a 453. The leader of the number of nuclear reactors is, of course, the United States. Then there's France, China, Japan, Russia, so on. India have several nuclear reactors as well. And then the champions around among those who are constructing the nuclear power plants and reactors. So China is building 13 nuclear reactors. Right now, China has around like 53, but then there's building even more. India is constructing also around 7 nuclear reactors. Russia is 6. So the nuclear energy is also growing as renewable energy.
What
And
about
then
your country?
we used to have one nuclear reactor, but it's also stopped because every reactor has its own lifestyle. So far, we stopped. It was actually a good reactor, which is the one that recycles the waste. It was also fast breeder reactor, but for security and safety reasons, we stopped. And now we are considering to build a new one, but maybe I don't know when, after 10 years. It's taking a long process. Yeah, so we have permanent shutdown, one reactor here in Kazakhstan.
Okay.
So nuclear share of electricity generation. So you know that France is the leading country for having nuclear energy. It's around 77% for producing. Then Ukraine, Slovakia, Hungary, Belgium, Slovenia. Maybe you can find your country here, guys. Those who are watching this presentation
No,
on YouTube.
there is India, not Indonesia. No.
Sorry. So China is only beginning of the at its beginning nuclear age. Currently, I'm sorry, that was wrong. There was 43 nuclear reactors operating in China, and there's 13 more coming. So this is nuclear reactors under construction in China, and you can see they expected to grid connection this year, 19, 19, 19, 19, like 6 reactors, or even 7 reactors, and then there are others building very soon. So we're increasing rapidly since China has also signed the what they call COP21, right? The document for reducing the CO2 emission. And then China is massively closing their power plants based on coal and switching to the nuclear. And there's a uranium price has increased since then because there's a huge demand is going on by this month, maybe this year expected to be the growth. The currently price is in US dollars per pound, so I switched to the converted to kilograms for those who use CI units. So it's around $63 per kilo of uranium. So those of you who love Marvel, I put a picture of the Thor. You know this Thor is like God, Germanic, and there's an element called thorium that have the same origin. So thorium-234 is a future nuclear fuel element. It's fertile, thus it may lead to uranium-233 production, which is fissile. So then we can use this uranium as a fuel. So then in future there will be thorium-uranium mixed fuel can be used. And currently India has a lot of supplies for having thorium. So most of the people are expecting that India will be a leader in thorium fuel production and also thorium nuclear reactor technologies.
But why thorium is the future? Is it like harder to process or less radioactivity or?
It has they believe it's having less of the waste. So the most consideration now for nuclear energy is having less waste as possible. So thorium gives less of the waste in the end of the fuel cycle, and then this waste can be also transferred to another uranium-235. So it'll be longer process, use more energy as possible from thorium.
Okay, and India will be the leader of that thorium fuel because they have the mining for thorium, or
They
why?
have they have supplies. They haven't started mining yet. I think they some of them started. There's a lot of research going on right now. I don't know, maybe it's south of India, maybe Kerala. I might be wrong.
Uh-huh.
There's a research for thorium reactor,
Okay.
and even I remember from guys from SNIM, they some of them were talking about the stash internship in Siva for thorium technologies.
In where? Sorry.
Комиссиат Energy Atomic. I remember almost SNIM students went to the stash internship in CUA. That's
Okay.
French Commission, Nuclear Commission, and
All right. Okay.
renewable energies. Yeah, so they have thorium resources,
Okay.
thorium researches,
Mm.
research. So briefly, almost done. It's about myself. I'm working as a manufacturing engineer. So we produce this kind of fuel assemblies. This is a company which is mixed joint venture between Kazatomprom, the Kazakhstan nuclear company, especially the Ulba metallurgic plant, with 49% of the China general nuclear. As I said before, because China is building the uh, reactors this year and next year, so there's a high demand of the fuel assemblies. And so they asked and joined to our factory to produce some of the fuel assemblies for them. So there's a picture from Automarino that I got from the website. Pretty much there's some references, and I really enjoyed giving the presentation. It was first time, and I'm a bit scared. I hope it was well, and I believe you understand a little bit better the fuel cycle in nuclear. Thank you so much, and I'm ready for your questions.
Thank you, Bakhtiar, for the presentation. And actually, I have a question for you. And the
Sure.
question is actually on the life cycle of the plant, not exclusively
Hmm.
on the fuel. So it's a really basic question. Like, imagine
Hmm.
that I want to commission a nuclear plant, and I on paper I sign it off today.
Hmm.
What is
Hmm.
the time that is needed from the date of signing till the date of commercial production of electricity?
I see. Well, honestly, I haven't experienced working yet with this process because it depends on different factors. In my country, it takes maybe 20 years to build first nuclear reactor because of economical reasons. In France, for example, there's a 58 operating reactors, but there's a one which is new generation, like perfectly well working, but it takes a long time to produce to connect it to the grid to commercially produce electricity. For one reactor, it's called Flamanville in Normandy, and there's been so many. It's been taking too long to produce, maybe more than 5 years. I don't know how long it will take because it depends on the country, depends on different factors. But if we're speaking about lifestyle of one reactor, it goes maybe around 50 years. For example, here I put a picture image of the France, which is 77%. But if you remember, Monsieur Macron said that they will reduce this percentage of the nuclear energy from 77 to around 50% by increasing the value of the renewable energies in France. So the share of the renewable energies in France will be increased, but it doesn't mean that they will only by increasing the renewable energies they will reduce the nuclear energy. The energy nuclear will be reduced by itself because the lifestyle of the operators. Most of the reactors in France are built around 60s or 70s, like of the last century. So pretty much this is like this year, next year, or next 10 years in France will be a lot of shutdowns of the reactor because the lifestyle need to be like stopped for the safety and security reasons. But of course, there's some EDF they proposing to extend the license, so maybe at least for a couple more years to produce energy. They believe it will be safe and ready to capable to produce energy. But also the future of the nuclear energy now is about stopping the nuclear power plants, nuclear reactors, as well as dismantling them. So there's several directions where students of studying nuclear engineering can almost study the waste management, they can study dismantling, they can study the nuclear production, maybe medicine. But also the future one is predicted is the waste management and the dismantling, decommissioning. Another question?
Yes, thank you. Well, there's some questions from YouTube. I'm going to ask them to you. First
Mhm.
of all, the question is, what is the percentage of uranium that is going for disposal after its first cycle?
You mean the disposal? Because first cycle we mean the depleted uranium
From the mining.
from the mining. Yes, like you see,
Yeah.
that's value, but it's not. We need to separate two terms: disposal and storage. So this is uranium-38 will go to the storage. It's not the waste yet. We consider it as depleted uranium. So then we can reprocess uh, with different processes, like to produce plutonium and use as energy. But I mostly talked about this like light water reactor, and there's only one type of the reactor. There's several more types, and some reactors like heavy water reactors like CANDU. These reactors exist in China, India, Canada. They can use uranium-238 as a fuel, so they don't need to do this all processes for uh, enrichment, conversion, etc. They can use directly the uranium-238. So specifically for the light water, we need to convert. So um, there's not so many percentage here being wasted from here. The most waste goes to waste to disposal, coming from the high-level waste after already the fuel assembly is when it's been used, like it burned out. I'm sorry for my English. I think it was clear as I explained.
No, it's really clear. Thank you. So actually, you were just talking about using uranium-238 directly as a fuel. Can you elaborate a bit on that?
Yeah, I tried. Well, there's reactors are different. They can be like pool type. They can be like loop type. And some of the reactors is called the CANDU. They used not uranium, but they used like I'm sorry, they used not just light water as here, but they used a heavy water. It's not H2O, but D2O, deuterium water. And this deuterium water is so condensed, so it can capable to transmit the neutrons in the reactor that way. So this it will be enough to start the production chain reaction in the uranium-38 because it's very hard to explain, but imagine that neutron that I said to start the reactor here, nuclear reaction, it passes through so fast, so this nucleus didn't affect and didn't start the reaction. So to make a reaction, we need to slow it down. That's why when the environment and media here around, it will be a heavy water, this neutron slows down very from being fast. It slows down because of the like friction through the heavy water. And at the moment touching to this nucleus, it will be slowed down that way, so it will be enough to start the reaction. So if it's uranium-238, it can be possible. But in a light water reactor, as I showed here, this one, this reaction may not happen because of the neutron is too fast and can pass through uranium-238. So it should be condensed to uranium-235 because they have different structures. And neutron touches the nucleus of 235, there's a high probability to start the reaction.
Oh, that's interesting. So it means actually the reactor that is capable of working with uranium-238
Yes,
are the ones that are more efficient in terms of using the fuel.
right. I agree with you. Good job, Stu. Of course, you're right. But the problem here that's it's very heavy. It's very expensive to get the heavy water. It also requires a lot of processes to produce. This is why most of the reactors they use this just simply water because it's cheap. maybe well-known technology to be used,
Okay.
and the process. Yeah, but of course the heavy water also is heavy water reactors are also well efficient.
Okay. Thanks.
Mhm.
We have another question, and the question is that you were talking about CO2 emissions from different, comparing CO2 emissions from different process energy production, notably how the emissions for nuclear, solar, and wind are. How can we compare them? But also, there's a question that when we are talking about nuclear, besides CO2, which are the other gases that nuclear produces?
I'm sorry, I didn't get the question.
When we are talking about emissions, we talked about CO2 emissions.
Right, right.
But
You mean?
beside CO2, what
Mhm.
are the other gases that the process of nuclear energy might produce? Or are there other gases that this process produces?
Well, there is no gases that being produced during the energy production, but of course there's some gases that can be produced during the production of the reactors for the fuel assemblies, etc.
Like,
Like,
can you elaborate on those type of gases?
let's say to make this mm, fuel assembly like this, you need to melt the elements to construct uh, the building. There's some gases maybe possibly, including CO2 and other elements. I don't know. It can be like sulfuric acid, SO2, uh, what's it called?
But
H.
there are no gases that are directly related to the fuel, that is uranium.
Yes, there's no direct gases that are being produced during this energy production. Mostly gases are being produced at the moment before like connecting to the grid. It includes the production of this reactor core, pressurizer, steam generator, etc.
I have another question. So you're saying that the mining, or let's say Kazakhstan, in the place you're working now, you're producing fossil fuels, right? But
Mhm.
then sorry, yeah, and then the so not fossil fuel, the nuclear fuel, and these
Mhm.
fuels are going to have to be transported to the nuclear power plants.
Mhm.
And let's say the place you are working. My first question is, what is the first destination? And the second is, how are those fuel transported? I mean, what is it that we have to think of when we are transporting this nuclear fuel?
Well, and all the entire process of the fuel cycle, during at each stage of the fuel cycle, there need to be high level of the security and safety for the environment and the workers. It should be well protected by using the special uh, sensors to show that there's no leakage and possible radiation coming out from this. And this is why they use mostly containers to transfer. To optimize the production line, they mostly build them next to each other. So, for example, if I say about in situ leaching, so they put the power plant, plant those who produce the U3O8 as a yellow cake like this. They build directly to the mines, and then this yellow cake being placed in a steel drum to be well closed and protected from leakage, and then they can be transferred to these production lines. And most of the production lines are located to each other. So if we're talking about the coming back to the previous question of Nipple, there's maybe some like chimneys that also can produce different gases as air pollution, of course, not besides the CO2, but they only related to the production of these fuel rods, fuel for reactors. So it's better to optimize. For example, the place where I'm working now, we produce the fuel rods assembly. So we're located close to the fuel pellets production, where the powders are coming from its yellow cake, and they produce this black dot fuel pellets like this. So then these fuel pellets are transferred to our plant, where we produce necessary fuel rods, etc. And then, as we finish up with the fuel assembly, then it can be placed into a well sealed and protected containers. Mostly containers are using lead as an element because it's a have high level protection from this possible radiation, and then this can be securely shifted by tracks and then to the railways to the necessary nuclear power plant, and backwards from nuclear power plants can be sent back to the reprocessing uh, power station. All right.
Okay. Yeah. Okay. Thank you.
Mhm.
Well, as there are no more questions, I would just like to ask you a last question before we close it. My
Mhm.
question is, after the cycle of after the nuclear power plant has finished its life, and we want to dismantle it, what
Mhm.
are the what happens with the, I don't know, all the metal and the concrete that has to be
Mhm.
dismantled, and
Mhm.
how long or what precautions do we need to take with the site where the nuclear power plant was built?
Okay. Well, it's a long process. This is why I said this is a future of nuclear energy. It's a dismantling. It's a new type of the major, which is will be very well requested in the world. So as we finished the burning out this fuel assembly, it's still hot, gives energy, not energy. It gives the radiation, and because there's a lot of bunch of processes going on inside of this, to from the production new radionuclides to another, there's a transform. So as long as we finished with shut down the reactor, we wait a couple of days, then it's still hot. While it's been hot, the cranes lifted up these fuel used assemblies and put it into the fuel into the pool. And there is a pool that contains in a separate building. It should be, it's not not here, but there's another building for the spent fuel. So the spent fuel stays in a pool of water for several years to cool it down and to stabilize the possible transition of the radionuclides. As long as it's stopped, then it can be moved to the reprocessing plant where the fuel rods are being cut into the um, into the like small pieces and then dissolve them into the in acid to separate some materials like uranium, plutonium again, and put them into another fuel as a MOX. And then the concrete, they also need to be like dismantled very carefully. There's also should be like time for filtration of the entire building. So basically they close the entire building and they put some inflow like air circulation, and outside for this like do some filtrations to capture all possible particles of the uranium, etc. So it should be done several times before this reactor can be opened for the environment. So there should be a lot of like dismantling process by process. It's very complex dismantling procedure.
So basically, it is a specialized field in itself.
Yes, it's different field. Yes, of course. This is why most of the reactors, nuclear reactors, are not being built on a new place. They're mostly built next to the used reactors, so to save some future work for dismantling. So if they stopped one nuclear reactor unit building, they built another one next to it. So it will be in future they can dismantle them both at the same time.
So, just maybe one last question. That
Uh-huh.
fuel assembly that goes into the reactor,
Yes.
said that the spent fuel has to be stored in the water for several years. But
Right.
during
Yeah.
the operation of the reactor, how long, like one spent fuel, how long can it operate producing energy?
So one fuel assembly mostly gives around like 1 year and a half.
Right, but then the spent fuel of those assemblies
Mhm.
are going to be kept in the water for more than the
Yes.
production
Yes.
period.
This is why the actual pool for the in a nuclear reactor is more larger than the fuel, the reactor itself. There's a huge amount of water, like pool, where it stopped. And then there's sometimes like temporary stops of the reactors happening for during the maintenance. because we need to at every cycle need to check the uh, well functioning of the all the process here. So we need no leakage, everything. So once in a while they stop the entire reactor to make some like check, a maintenance check, while the other fuel still being stored in the pool.
Okay.
So it's been well designed to make sure there's no extra used fuel assemblies
Yes.
over volume to the entire pool.
Right.
Yeah.
Okay. Yeah. Well, it's interesting.
Well, thank you so much, Bhaktiyar, and I think that's all the questions we have. And we really thank you for talking to us today about the cycle of nuclear fuel. And there's a lot of things we get to learn, a lot of clarifications. To be honest, that we get today based to nuclear fuel, because it's true. Because most of us work in the sector of sustainability, may it
Mhm.
be environment or energy or transportation. To some extent we sometimes become anti-nuclear, and I think this presentation's objective was not to change this position, or was not to create a debate on whether nuclear is a good alternative or a good energy source or not. But I think this presentation has helped us to clear a lot of concepts in our mind, so that we can go ahead from there.
Sure, of
So
course, I agree with you. So I believe also in the sustainable lifestyle. I highly support the all technology and beginnings for the renewable energy in future. And at the same time, I support nuclear energy as long as it reduces the nuclear waste and keeps the environment safe. So for us now, because we already produced for the last 30 years the waste disposed, I believe in future that new technology will transfer those technologies who can reuse this waste disposed and can be used for good for the future as energy. And at the same time, I wish you all the best, guys, in sustainable lifestyle. Do your research, do your job well. Thank you for your time for this Sunday time, 1 hour for this presentation. I believe it was useful for all of you. Sorry that I couldn't clear maybe explain it deeply, but this nuclear energy is a very complex scientific field.
Yeah.
So I try to do it as much as shortly and briefly explain to you in this way, so it will be clear and understandable for everyone. I really appreciate your questions; they were useful. Thank you for your time, Astu Nipun. I wish you all the best. I believe that we'll meet again more and more, quite often with the Emanate community.
thank
Thank you
thank
so
you.
much. Have a good Sunday.
Thank you very much, everyone. Have a good day, or a morning, or an evening, depending on where you are. And thank you for joining us today. Bye bye.
Bye.